So one of the things that we've learnt by now is that our field does not create a single particle state with probability 1. Now, this is not great. We actually want our field to create a single particle state with probability 1 when, for example, we are calculating a correlation function and the field acts. We really want it to create a particle. We want to be certain it's created a particle. So we want to create a particle with probability equal to 1. So because of that, we'd like to introduce a physical field for which 1 is equal to K1, 5 naught, naught squared. And this would now be our physical field. Okay, so how is this related to the field that we had appearing in our Lagrangian? Well, if you look at the top equation of the page, it's quite clear that if we set our physical field by P to be equal to Z to the minus 1/2 phi, or equivalently, we could say that phi is equal to Z to the 1/2 the physical field, it's clear that this will accomplish it. Okay, and so let's just talk a little bit more about this. We have already agreed and checked, actually in quite a bit of detail, that Z lies between 0 and 1. What that means is, if we study Z to the 1/2, well, this will lie between 1, Z to the minus 1/2. This will lie between 1 and infinity. So what that means is our field, phi p, the physical field, is actually bigger. The field strength is larger than the field strength of phi. And this makes sense. Our field phi is creating a single particle state plus some multi-particle garbage. We're increasing the field strength so that the amplitude with which we create a single particle state, that probability is equal to 1. So what we're learning here is something that in retrospect is not too surprising. We said that the parameter m and g were not the physical mass and couplings. We needed to introduce a physical mass, m phys, and a physical coupling, g phys. We're now learning that the field itself, the field strength of it, is also not physical. And we have to renormalize the strength of the field. And the way that we renormalize the strength of the field is summarized by these relations in that black box. And now it should be clear to you why Z is called the wave function in normalization. This is the thing that relates the field strength in the model to the physical field strength. So our Lagrangian, which used to be 1/2 d mu phi minus 1/2 m squared phi squared minus g phi to the 4, it now becomes L is equal to, it will be, let's put the 1/2 there, Z, then we'll have d mu phi physical, d mu phi physical minus m squared phi physical squared minus, it'll be Z squared g phi physical to the 4. And we've now expressed our Lagrangian in terms of the physical field strength. Okay. Good. So what you see now is that our theory has 3 parameters. These are Z, M, and G. We want to express these in terms of, now before Z was the probability of creating a single particle state. Once we've renormalized our field, we create a single particle state with probability 1. So I'm putting the 1 there. It's of course not a parameter, but I'm putting it there to remind you that this is how we determine the strengths of our physical field. We say that we want our physical field to create a single particle state with probability 1, and that's the one that I'm writing there. And then we also have the physical mass and the physical coupling. To express Z, M, and G in terms of 1, M phys and G phys, it means we need 3 equations. Okay, we've got 3 equations which relate 1, MP, and GP to Z, M, and G. We can solve them and express Z, M, and G in terms of 1, MP, and GP. Okay, so let me tell you what those equations are. Now these are often called renormalization conditions. I'm going to call them matching conditions because they allow us to match our theory to nature. So what are the matching conditions? Well, we know 2 of them. So let's write those 2 down, and we'll come back and complete these matching conditions a bit later. So the first condition is the Fourier transform of the 2-point function has a pole at p squared is equal to mp squared, the physical mass squared. And then the second condition is that the residue of this pole is 1. Let's discuss the second condition, okay? So what do I want to do? Well, I want to take this box over here, and we're going to rewrite it slightly, okay? So let's copy this, duplicate, let's move it down, good. So let's put it over here, and let's see. Okay, so what do I want to do? I would like to express things now in terms of the physical field. So I'm going to modify this formula in red, okay? So I would like this to become the physical field. I would like this to become the physical field. If I do that, and let's maybe work out now what the 2-point function is, what do I need to do to turn the field into the physical field? I need to multiply by z to the minus 1/2. So I need to multiply by z to the minus 1/2 for both of the fields. So I'm multiplying by z to the minus 1 on the first term and z to the minus 1 on the second term. So once I've multiplied by the z to the minus 1/2, I lose that z and I lose that z. And now you see very explicitly that indeed the residue of the pole is 1. You get that by looking at this term that I have just circled in green. Looking at that term there, the residue of the pole is I, and the pole sits at p squared is equal to mp squared. So these are the first 2 conditions that allow us to start expressing z, g, and m in terms of 1, mp, and gp. Okay, so just to be completely explicit, so what would you do? How would you use these conditions? Well, you know how to calculate the 2-point function. You do it by drawing Feynman diagrams. So, here we go. I'm going to draw it to 2 loops. So you take all of these, you would add them up. Then once you've got this function, calculate its Fourier transform. Once you've calculated the Fourier transform, look for where the pole of this function sits. Set the pole equal to m physical squared, and then work out the residue. and set the residue equal to 1. So that'll give you two equations, and those two equations will be written in terms of G, Z, and the physical mass. So now there is one other thing that we should clarify, and we've now changed our Lagrangian because we've written it in terms of the physical field. So what are the Feynman rules for this new Lagrangian? Okay, so let's just write those down, and it'll be useful to have the Lagrangian in front of us when we try to do this. Okay, good. Okay, so I'm just going to say how the Feynman rules change. How the Feynman rules change when we change phi into the physical field. Okay. Oh, this is not the whole Lagrangian. Sorry about that. Yeah. Okay, so let's just correct this. Let's just put everything in. So we'll have a minus m squared. We want phi p. Here there should be phi p squared, and then minus g z squared phi p to the 4. Let's just check. Good. Okay, that's perfect. Okay, so here is the first change. There's only two changes, but here's the first one. So remember what we had for vertices. So we said when we've got a quartic vertex, well, it lives somewhere, there's an x. And we said that when we translate this into math, we've got a minus ig, we've got 4 factorial, and then we need to integrate over the position of the vertex. Well, if we look at the Lagrangian, there's now a z squared sitting there when we've written things in terms of the physical field. So we need to include a z squared into that Feynman rule for the vertex. The other thing that changes is, remember we had the rule for the propagator, and we said that what this gave us, it gave us g of x comma y, and what this was equal to, it was equal to an integral before p over 2 pi to the 4. It was an I over p squared minus m squared plus I epsilon, and we had an e to the I p dot x minus y. Now, where did we get this g of x comma y from? This was by inverting the quadratic terms. So invert quadratic terms in the Lagrangian, okay? But the quadratic terms in the Lagrangian have changed because, look, we've now got a z multiplying the quadratic terms. So when we invert those, we'll now get a z to the minus 1. So for each line in the Feynman diagram, we now also have a z to the minus 1 appearing. So those are the only changes to the Feynman rules, but those are two changes that we make. Very good. Okay, so just to summarize, where did this extra parameter came from? Well, we've realized that the field that we have in the Lagrangian is not actually the physical field. Why? Because we want the physical field to create a particle with probability 1. So we had to rescale our field. We had to rescale it by the wave function in normalization. And that is why Z gets the name of the wave function in normalization. It renormalizes, or it modifies the field strength into the physically observed field strength. Great. We've got one more renormalization condition to spell out, and we'll do that next.